Hey everybody, today we're going to talk about sound intensity problems. And there are two different types of sound intensity problems. One's involving the decibel scale and ones that don't. So let's talk about the decibel scale first. I'm sure you've heard about the decibel scale. You know, something is 60 decibels or 100 decibels or 90 decibels. What the decibel scale is, it's an artificial rating system. It's a way for us to take sound intensity levels, which typically are very, very low numbers, and put them into a system that makes sense for us. So it starts with 0 decibels, which is the lowest possible whisper that you can hear. And then it runs up from there. The decibel level of 120, for example, that is called the threshold of pain. That's where we start to get pain in our eardrums. It goes up from there to the threshold of damage, where it will permanently damage our eardrums. So how do we figure that out? Well, let's do an example problem. I'm going to do a conversion to the decibel system and then from the decibel system. So let's say that we're told that we have a sound that is an intensity of 3 times 10 to the negative 6 watts per meter squared. Watts per meter squared is the unit of intensity. It's basically telling us the power going through an area. So we want to figure out how many decibels is that. Well, we're going to use our decibel formula. My decibel formula looks like this. The number of decibels equals 10 times the log of our intensity divided by what's called the threshold of hearing, I.O. I.O. is a constant, 1 times 10 to the negative 12th watts per meter squared. Yes, I will give you that constant. You don't need to memorize it. So now we're going to plug in to figure out how many decibels is this very low number. Okay, so I'm going to do this in stages. I'm first going to divide 3 times 10 to the negative 6 divided by 1 times 10 to the negative 12th. When I hit that into my calculator, ta-da, 3 to the negative 6 divided by 1 to the negative 12th, I get a very big number. I get 3 million. Okay? Now make sure you're hitting your proper exponent key in your calculator. I'm now going to take the log of 3 million. That's why in the email yesterday I told you, make sure you know how to do this. Now, for most calculators, you're going to say log 3 million. Okay? That gives me 6.48. Ten times 6.48 is 64.8, and that's decibels. Okay. Now, what if you're given decibels?
you can keep going. It's just that if you're gonna pause so I can focus, it's probably better if you don't pause right in front of it.
Well, I was trying to get you to focus on this.
Well, you also need to have that in front of the camera, which is here. Hello, class, and not over here. Okay, intermission over.
All right, so now let's go from decibels to regular intensity. So now let's say we're given a decibel level. Let's take one that's pretty loud. The fire alarms in our school are 95 decibels. I know, I've measured them. So we want to now go from 95 decibels is how many watts per meter squared. That's going to be pretty important because when we do our actual intensity problems, we're going to want to figure out, well, our answer in watts per meter squared. So let's see. 95 decibels to watts per meter squared. I'm going to use my other formula that was in my Nearpod presentation, which is this. Watts per meter squared equals the anti-log of my decibels over 10 times IO. Okay, so again, I'm going to solve this in stages. So my IO is 1 times 10 to the negative 12th times the anti-log of 95 divided by 10. Well, I can do 95 divided by 10 in my head. That's 9.5. So I'm now going to take the anti-log of 9.5. So to do that, I'm going to have to use my inverse log key. Now, depending on your calculator, you're going to do that a variety of different ways. Okay, my calculator, it's a simple thing of going second log. You've got to check with your calculator as far as how you put that in. So I'm going to put in second log 9.5, and that gives me a pretty big number. That gives me 3.16 times 10 to the times 10 to the 9th, which I'm now just going to multiply by my 1 to the negative 12th. And I get that this is equal to 0.00316 watts per meter squared. Okay. So that's how I do my decibel conversions. Now, a couple of things about the decibel scale. Number one, it is a logarithmic scale, meaning that just going up a little bit of intensity is going to give us a large jump in decibels. For example, we saw that we had here a very low intensity. Okay, that gave me my 65 decibels, which is about conversation level. I still have a low number of watts per meter squared, okay, but I am three decimal places higher, so that's 1,000 times greater, and I'm at 95 decibels, okay? So a logarithmic scale, meaning 20 is 10 times more powerful than 10. 30 is 100 times more powerful than 10. 40 would be 1,000. Okay? Okay, so now let's talk about how we solve a problem dealing with intensity, not including the decibel scale. One of the important things to remember about sound intensity is that it is an inverse square relationship. The further away you go, the more dramatically lower the sound is. So let's take this problem here. A cannon fires with 100 watts of power. That's a lot of power for a sound wave, okay? But cannons are pretty loud. What is the sound intensity 10 meters away? And then what is it 50 meters away? That's so we can compare the two sound intensity levels. So our formula for sound intensity is this. I equals power divided by 4 pi r. That's our surface area. So let's see. We first got 100 watts of power over 4 pi times 10. Okay? Because we're 10 meters away. Put my little meter in there. Actually, it's squared. Okay? So 10 squared is 100. 100 divided by 100 is 1. So 1 over 4 pi gives me 0.0796 watts per meter squared. Now, if we remember from the last problem that we did, when we were converting from decibels to watts per meter squared, 0.0316 was 95 decibels. So we are twice that, actually more than twice that. We're 20 times that. So this is going to be a really loud sound, okay, if we're close by. So actually, let's do a quick conversion. So what is that in decibels? 10 log I over IO. So 10 log 0.0796 divided by 1 times 10 to the negative 12. Log of my answer. That gives me 109 decibels. That's really loud. That's getting close to your threshold of pain. Okay? So now let's do the same problem, but when we're 50 meters away. So the same power divided by 4 pi times 50 meters squared. That's equal to 0.00318 watts per meter squared, which is about what we got on our last problem. So this is approximately 95 decibels. So just being 40 meters away dropped that sound down in intensity, well, an awful lot. Okay, here we're not even a 10th or a 20th of what we were close to the sound, showing that sound has an inverse square relationship. Okay, that's as far as I want to go today. If you have any questions, please send me an email. Tomorrow we're going to talk about the Doppler effect, and I will see you a little bit later. Have a great day, Township.